Hello, in section 9.2, we are covering direction fields, and direction fields, which are also known as slope fields, help us visualize the shape of the curves that solve a differential equation. It is easier to create these graphs by focusing on specific areas of the Cartesian plane. For example, the axes. It's also good to look at the line y equals x and the line y equals negative x. And then to also look at the regions in between all of these. We're going to be looking at regions 1 and 2 here. So, our first example is to consider the slope field of the differential equation dy dx is equal to x squared minus y squared. What can be said about the slopes? First of all, on the x-axis. So on the x-axis, if you look at that, you know on the x-axis, y is equal to 0. So in that case, dy dx would just be x squared, right? Because x squared minus 0 would be x squared. So what that means is when x is 1, for example here, 1 squared is 1. So we would have a slope of 1 on the x-axis, and as x gets bigger, our slope is going to increase. There's a slope of 4, here's a slope of 9, and so on. So our slope's going to increase. It's going to look like they're vertical lines, but they're just really, steep slopes. So if you look at the other side, I was just looking at the positive values of x. When x is 0, guess what? The slope is going to be 0. So you're going to have 0 there. And then when x is negative 1, when you square it, it's going to become positive. So you're going to have slopes that are positive again, and they're going to get steeper and steeper as you move to bigger values. So that is on the x-axis. If we look on the y-axis, where x is equal to 0, dy dx would then be 0 minus y squared. So the slope is going to be negative. You guys, if we were in class, you would catch me on that. Negative y squared. So on the y-axis, when y is 1 here, my slope is going to be 1 squared is positive 1, but since we have that negative in front, I'm going to have a slope of negative 1. And then when y is 2, I'm going to have a slope of negative 4. And these slopes will end up getting steeper and steeper as well, but in the negative direction. Same thing with these values here, negative 1, negative 4, and negative 9. So that's what our slopes look like, our direction field looks like just on the x and y axis. So you can see that these slope fields take time to think about as you're creating them. Luckily, we have some tools that we're going to look at later, but let's move on to the line y equals x. And so on y equals x, our derivative is going to be x squared minus x squared, because y is now equal to x. So our slope is going to be 0 everywhere on this line, y equals x. My slope is going to be 0. And what does the slope of 0 look like? I'm going to change colors here so that we can just see all the zeros. My slope will always be 0 on this line. I've got horizontal slope fields there. Cool. And similarly, on the line y equals negative x, notice dy dx will be equal to x squared minus negative x quantity squared, which again is 0. So on the line y equals negative x, we'll also have horizontal slashes there. So there's the line. Oh, don't mind me. I actually graphed y equals negative x first, and then I did y equals x. So my bad, flip that. Oh. Do I start over? Keep going. Okay, so know that I was bad. When I said the line y equals x, I went like this, but this is the line y equals x. Everybody knows that. So my apologies. This is a little wrong, but we'll be okay. Okay, so there's the slope field still the same. Let's look at region 1 now. So when you look at region 1, that's this area over here in between the line y equals x, there's a line y equals x, and the x-axis. So region 1 has values, any point in this region, we know that the x value is bigger than the y value. So that means that x squared is going to be bigger than y squared. So remember, our dy dx is x squared minus y squared. So if we solve this equation over here, x squared minus y squared would be bigger than 0. So dy dx is going to be x squared minus y squared, which is bigger than 0. So all my slopes in this region are going to be positive slopes. And as x gets bigger, the slopes will get bigger. So I'll do these in red. So we've got positive slopes, and they actually get really big pretty fast. Now looking over at region 2 here. So region 2 is between the line y equals x and the x-axis. And the y-axis, my bad. So between y equals x and the y-axis, here's region 2. So if you look in region 2 and you think about points in region 2, in that region, because that's negative land, we have to think about the absolute value. So the absolute value of x in this region is going to be less than the absolute value of y. So the x squareds are going to be less than the y squareds. And that means that x squared minus y squared is going to be less than 0. So all of my derivatives are going to be negative. So in this field, using those red slopes, so I'm going to have negative slopes, and they're going to get more and more negative pretty quickly. Again, they'll look like vertical lines. I would continue this process. Again, you can see where it's quite tedious. I would look in this region, how are my x's compared to my y's? I would look in this region and so on, all these regions individually, and start marking my slope field. But what's awesome is that we now have technology, and we all know about Joel's favorite place, Desmos. So going into Desmos, I've got this on the Desmos Den, and I've plugged in the equation x squared minus y squared. That's our derivative. And notice g of x is equal to, I just did something. G of x is equal to the derivative dy dx. So if you look at, this is the direction field that I just plotted, but just on a much grander scale. It goes all the way out till 10. And again, look at how steep those slopes are. Positive slopes this is our region 1, and over here was our region 2, and here's all those 0. There's the line y equals x, and there's the line y equals negative x. So you can see the big direction field in on Desmos. Oh, I should pause. So now, while we're in Desmos, let's look at some other functions that we know a little bit about. So I'm going to look at the function, or look at the differential equation, dy dx is equal to y. So we already know whose derivative is itself. And there's a reason why the slope field looks the way it does here. If you see the flow of what's going on here, what does this flow look like? Going down this way, it should look like an exponential equation. Why? Because e is its own derivative, correct? So if we're looking at dy dx equals y, we're looking at an exponential function. Q. So let's look at another one. How about the differential equation? dy dx is x divided by y. And take a look at this direction field, and what do these graphs remind you of? And if you think back to your Algebra 2 class, these look a lot like hyperbolas. So, for example, I see a hyperbola here, or you've also got some hyperbolas on the side. So this differential equation is a family of hyperbolas is the solution to that differential equation. Want to do it again? We'll do one more. So erase that. Let's look at pretty similar to this one, except let's make that a negative x over y. And you may, I forgot Desmos is so fast. I was like thinking you might want to guess what this is going to look like. But you've got it. It looks like a bunch of Mars.
Someone who hasn't shaved in 3 weeks.
What do you think this is, Mars?
Circle?
It looks like a circle. Absolutely. 3 cheers for Mars. Hip, hip. Hooray! So do you see all the circles? So the family of circles would solve this differential equation. Once you're given the initial value, if you're given some more information about the particular function, you can figure out which of these circles is the one that models what you're looking at. So let's now move a little bit back to the calculus behind this, and let's look at that circle differential equation. So if we look at the circle differential equation, and we've got dy dx is equal to negative x over y. We can remember when we were working with Mr. Body, who killed him, we talked about separable differential equations. So I'm going to multiply both sides by y dx. And so I'm going to end up with y dy is equal to negative x dx. So this is a separable differential equation. This is in section 9.3. Separable, I'm hoping I'm spelling this right, differential equations. These are the ones that we can solve at the ready, because all we need to do is integrate both sides. And when you do that, on the left side, you're going to get y squared over 2. And there's technically a constant there, but we'll just use a constant over here. And you've got negative x squared over 2 plus some constant. And notice when you add x to the other side, you're going to get x squared plus y squared over 2 is equal to c. And so x squared plus y squared is equal to 2c. There we have the equation of a circle. So that is why the slope fields all look like a family of circles. If you not if you want, I encourage you to keep checking out Desmos, that slope field generator. What do you think the graph of the slope field for dy dx is equal to x is going to look like? What family do you think will be for those differential equations? And have fun.